Okay, so I think we'll start about now because it's almost the right time. So I guess first of all I should point out this is the presentation for Earth Sciences. If you're expecting a different presentation, then this is your opportunity to get out now while you can. Otherwise, you've got, I guess, 40 minutes of Earth Sciences, which should be awesome. So we've just got some pictures rolling through here of some of the things or some of the places our students go on fieldwork as part of our degrees. So this is a really important part of, I guess, an Earth Sciences education. So I guess Earth Sciences is almost kind of unique amongst university degrees in that we spend a huge amount of our time outside in the field making observations. So I'll come on to kind of the details of some of these later on, but it's basically, if you like science, okay, all kinds of science, and you like the outside and care about the Earth, then you're in the right room, which is kind of pretty good. So if I move on to what we're going to be talking about, let's say, I should also point out this session is being recorded, so if you at any point want to the recording of this, if you email me, and my email address is earth.sciences@ed.ac.uk, it's on all of the kind of prospectuses, flyers, and all that kind of stuff. I'll send you a link to the presentation, and also there's the lecture, an example lecture later on today at 2:50, I think, about coral reefs. I can make that recording available as well to you if you want it. So today, for this talk, we're going to hopefully, some of you will already know what Earth Sciences is, some of you won't, so I'm going to briefly explain what Earth Sciences is, and then go on and basically try and convince you that Edinburgh is a good place to come and do this, which hopefully should be very easy. This is an example of a lecture theatre, very like the lecture theatre you're sitting in today. And the reason I kind of show this is that everything in this room, okay, everything in almost any room, relies on Earth Sciences because everything has been either made of stuff that has been dug out of the ground, okay, so the plastic floors, the metal that makes up the seats, all that kind of stuff. The lighting is powered by energy, which I guess in Scotland doesn't really come from fossil fuels much anymore, but even kind of the renewable energy resources, Earth Sciences play a huge role in making those things happen. Even the wood that the desks and stuff are made from, understanding how critical elements like nitrogen and phosphorus get from the solid Earth and cycle through the biological kind of environment and are able to produce crops of trees or crops of stuff we eat. These are all kind of Earth Science-y type questions and problems. So Earth Sciences is really also about looking at the Earth and understanding it. And we look at it in a number of different ways. So we look at it with our eyes, because that's the cheapest way of looking at the Earth, and making observations of rocks, a hand specimen scale or kind of a mountain scale. And from those observations, inferring things about how the planet works. So why do we get volcanoes in some areas? Or why do we not get volcanoes in certain areas? Or what's the hazard from earthquakes in a particular region? We also use a variety of physical sciences to look at the Earth. So it's not just with our eyes, we also use remote sensing. I guess this laser pointer is pretty much useless, but the picture of the Earth that's got the clouds on, that's a remote sensing image of the Earth. Also the one that's got the colours in the ocean in the bottom left. That's a satellite that's looking at the colour of the ocean, and we're finding out about where the biological activity is happening and understanding why we don't get life all over the ocean. Why is it concentrated in these certain spaces? There's part of an Earth Sciences problem. In that case, it would form part of our environmental geoscience degree. We also take kind of indirect observations of the Earth. So we've got a map of the gravity field of the Earth. This kind of oddly shaped potato thingy is actually the Earth. We also use physics and chemistry, not just to look at the Earth, but to model and understand it. Okay, so we're using tools like seismic waves going through the Earth to make an observation of the internal structure, but then we also might use a physical model to basically build a model of the Earth in a computer to understand, see if we can make essentially a synthetic version of the Earth to match the observed So we're basically using tools of science to make observations, but also to model. So this is, I guess, an example of one of these ways that we're using observations. So this is a map of the observations of surface temperature relative to the pre-industrial period. And you can see that the planet is a lot warmer now. So that's kind of an observation side of things, but we might also want to understand not just the global temperature rise, but why certain regions of the Earth are warmer than others. Okay, so why is the Arctic warming more rapidly than the rest of the Earth? Why are there regions in the ocean which have not suffered, or not so much suffered, but not experienced warming? Well, there are actually regions of the oceans that have cooled. So in this case, we have to build models of the Earth using our understanding of the physics, using our understanding of the biogeochemical cycling, that will tell us about how the carbon cycle is changing in these different regions, and might help us try and explain why certain regions of the world are cooling more rapidly than others, or warming, definitely warming more rapidly than the others. So to summarise what the motivations for doing earth science is, most of the lecturers, most of the people that are engaged in the research are really actually interested in how the Earth works. Just as purely as an intellectual activity, we're fascinated by the Earth in all its complexity, and we really want to figure out what's going on. But that does not pay the research bills. So we have to justify our existence in other means. Natural hazards form quite a huge part of that justification. I mean, it also helps us understand how the Earth works if we understand how earthquakes work, what are the drivers behind that's actually stressing the plates, what are the physical mechanisms of failure in rocks, and how does that help us predict or at least forecast which regions of the Earth are hazardous or not. So this is an active area of research in the department here. So after an earthquake goes off, there's a huge release of stress, but that release of stress will change the stress field in other parts of the Earth, increasing or decreasing the earthquake risk in those regions. And feeding that into basically hazard models and interacting with effectively policymakers is a really important part of earth sciences. The resources and energy kind of bubble there very much used to be geologists going out and go, dig a hole there, you find some oil, or there's a big pile of coal over there, I bet you dig up, you make loads of money. That is less so in the current, I guess, climate, quite using the climate in the two kind of meanings of the word. But we still do resources and energy, but it's much more broad now in terms of renewables, in terms of wind, tidal. We still need to understand the Earth that infrastructure is built on. We need to understand how they change the environment, particularly things like how the hydrological cycle will be changed, or the hydrology of a kind of like a peat bog will be changed if you build lots of wind turbines on it. And also the resources part of it. So everything in the room is from the Earth. So we still need to look for those things. We still need rare earth elements to build magnets to make these wind turbines or to make fancy things in our phones. So finding that material and also dealing with it in an environmentally responsible way. So this last bubble, the cleaning it up, making sure our resources are used responsibly and disposed of and recycled responsibly is again, a really big part of what earth sciences is, but also where our graduates end up going. Okay, so we're going to move on now and talk about why Edinburgh and also some of the specifics of our individual degree programs. So Edinburgh is basically where the subject of earth sciences, specifically the subject of geology, began. So one of the really good things about coming to study at Edinburgh is that you can go to all of the places where the science was figured out. So we have sites even within the city of Edinburgh in Holyrood Park and on, this is the Castle Mound, which is an old volcano, where people figured out the concepts of older rocks are at the bottom, younger rocks at the top, but also that you can get rocks injected in between layers of sediment. So we use these kind of historical kind of sites as part of our teaching, and that's really quite useful. It's very engaging for our students. But it's not just Edinburgh. Scotland itself, as a whole, is fantastically geologically diverse. So coming to a university in Scotland, you have all of this fantastic variety of geology on the doorstep. So each of the different colours, except ignore the red splotches, they're granites, but all the different kind of stripes of colour going through Scotland here are different kind of geological terrains. So what this means is these are basically a different kind of environment of the Earth's kind of system that's been kind of like added together as the continents have kind of drifted apart and smashed up back together again. So up in the Outer Hebrides, you've got what we would call the Lewisian terrain, which is from Lewis. And that's basically a fragment of the deep crust. So it's part of the deep Earth, which has been exhumed, and we can basically peer inside the Earth by visiting up there. The next dark brown band and the orange band on top of that, that's basically the core of a mountain chain. So it's very much like going to the Alps and digging away all of the mountains and looking at the structure of the inside of that. So basically how mountain building worked was first figured out up in the highlands here rather than in the Alps. Southern uplands is a terrain which is basically built up of deep sea sediments that have been compressed and folded and thrust up. So the modern environment that's kind of like is a little bit like the island of Barbados. Okay, it doesn't have the coral reefs in Scotland. Scotland does have coral reefs currently off the Outer Hebrides. They're very beautiful. They're deep sea corals. We're actively researching them in the department here at the moment. But the southern uplands don't have any of those, unfortunately. But and we have a sedimentary basin in the Midland Valley. Kind of, this is an analogy of what's happening effectively in the North Sea or in the East Africa Rift Valley at the moment. So we've got the East African Rift Valley is effectively just like the Midland Valley of Scotland. So we have volcanoes. There are volcanoes, same kind of volcanoes we have in Africa. We have in Scotland. In fact, in Edinburgh. Okay, so these are just some examples of some of the places that we go on our field teaching. I think there's another set of dots to come as part of our courses. Because we're located in Scotland, we're visiting all these places are very, very easy to get to. We also go to places in England as well, just to keep it diverse. And we also take our students abroad. And the abroad field trips are not just to go abroad because it's fun and sunny. It's because some of the processes that are going on here are no longer active. Okay, so fortunately there are no active volcanoes in Scotland. So if we want to go and see an active volcano, we have to go to Iceland. This is the map of Edinburgh. You can see, you might be able to make out. If I maybe make it a little bit darker in here, this is always risky because then quite often all the lights go off. Ooh. Look at that. You can see our volcano of Holyrood Park, kind of in the centre here, and this is just to show where the teaching will happen around Edinburgh. So some of the teaching will happen on Holyrood Park. I recommend walking up to this bit here if you want a nice view of the city. But we're based down here at the moment in the King's Building campus. In the first year, some of your lectures will be down here. Some of them will be in the central area. In the third and maybe fourth year, you might also have some lectures in the geography department, which is based in Drummond Street. And you will most likely live either in Pollock Halls, which is the kind of the main catered student accommodation, or somewhere around in the nice part of Edinburgh here. Now, we are not a single campus, so you will have to move around the city. It is actually relatively easy to do so. There is a shuttle bus that runs between these, which is free for students every 20 minutes. And it takes me to cycle from this building here to the library, which is there, 8.5 minutes. Okay? And I ain't Chris Froome, so... so there you go. So it's very easy city to get around. Cycling around the city is very, 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 very good. It's not as hilly as people make out, as long as you cycle around the volcanoes and not over the volcanoes. It's fairly easy city to get around. So this is this historical aspect which I kind of alluded to earlier. And so basically, so some of these guys here are the founding fathers, and they were fathers. There were no founding mothers at the time because science was very much a male-dominated activity. It is no longer. So these going to the places where these guys figured it out is really, really engaging. As a lecturer, it's really exciting to go to these places, and I imagine our students are pretty excited as well going on. So this is an example of one of these localities. This is a place called Sicker Point. You might have heard it as sometimes called Hutton's Unconformity. So James Hutton was, I guess, one of the first geologists. And he went to this place, and this is one of the places where he figured out that the age of the Earth must be really, really old. So previously, there were estimates of the age of the Earth which were effectively based off the Bible, which were somewhat inaccurate, of around 7,000 years, 6,000 years maybe, I can't remember. But he figured out that in this site here, we've got a series of rocks that were laid down as sediments. That means they must have been laid down in horizontal layers. But at this site, you can see that they've been tilted almost vertically. Okay, so that there's some period of crustal deformation, be squeezing, a very cataclysmic event maybe. But then he also found on top of these rocks another set of sediments that were laid down horizontally at a different angle. So his inference was that there must have been some enormous period of time in between these two events for the rocks to erode down, okay, and then be deformed. And then the next crucial piece of information that he spotted at this locality is that those rocks themselves that are on top are also tilted. They're not laid down horizontally. So there must have been another cycle of deformation. And out in the sea, there are more sediments being deposited. So his inference here was there's a never-ending cycle of sediments being deposited, crushed together, deformed, eroded, sediments being deposited. And his inference was that cycle effectively went on forever. So that his inference that the Earth had an infinite age. Now, we know that to be incorrect. But just from really simple observations of rocks in the field, we're able to draw some quite profound implications and conclusions. So that's not the reason why I'm showing you this slide. So some of these guys were important scientists. So James Hutton, Charles Lyell, founding fathers of geology. John Murray was one of the first oceanographers. And Arthur Holmes was one of the founders of actually dating rocks radiometrically. So it's really fantastic to have these people having been at Edinburgh. I mean, they have no bearing on teaching now. They are very much dead. But the person I want to point out is this guy in the middle, John Playfair. Okay, so John Playfair, not a scientist. Okay, so he was around at the same time as these guys here during a period of the Scottish Enlightenment, which was a time when basically science was becoming more important in civic life. Okay, so people were not just taking kind of the word of the Bible as literally gospel, but they were thinking for themselves. They were basically developing the scientific method. And this guy, well, basically these scientists were at the forefront of that, but they were scientists. So they wrote the dullest possible books you can imagine. Really impenetrable text of detailed observations and conclusions. What John Playfair did was he got interested in this science, okay, and he wrote effectively popular science books, okay, and he gave talks to kind of the rich and the do-gooders of Edinburgh society, and he popularised the science. So without that, okay, the scientific revolution of the Scottish Enlightenment wouldn't have happened. So the point is that act of communication of science is really, really important. And we recognise that, and we embed it throughout our degrees. Okay, it's that aspect of communicating your ideas, either in written form, verbal communication, other kinds of presentations. That is really important. We have an optional course in the fourth year of our degree programmes called Geoscience Outreach, where students are able to take something they're interested in and communicate that in some way that they're interested in to the public or to a group of policymakers or to a bunch of school kids. It's a really important aspect of what we do in our degrees. Okay, so we're not just educating you as scientists, we're trying to educate you as useful communicators as well. So just to point out that it's not just old dead white guys, we have loads of, well, so one of the things about Edinburgh is we're a really big department. It's one of the largest collections of earth scientists in the UK, which means we have a really broad range of expertise across different fields. So we've got people looking at climate science. So Gabby here, one of the lead authors of the IPCC report on climate change, recently elected as a Royal Fellow, a Fellow of the Royal Society, not a Royal Fellow. You have to be royal to be a Royal Fellow. She's not. But she is a fantastic scientist. We have Antarctic scientist Pete Nino, who's won the Polar Medal. is looking at how glaciers kind of are responding to climate change. We have people looking at the coral reefs, looking at fossils, paleontologists, huge range of world-leading academics. And yeah, that's great for research, but this also feeds into our teaching. So it's impossible for any of these people to be hired by Edinburgh University unless they have demonstrated that they are committed to teaching. It's like a rule we have. Which is kind of quite nice to have these really good academics that are fully engaged in teaching. But also by having a really broad range of researchers, it also enables us to offer a broader range of higher level courses in the 4th and 5th year. So if you were at a smaller university, the choices that you would get might be more limited by the interests of the academics of the department, whereas here there's a much broader range of stuff that will be available to you in the 4th and or 5th years. I won't dwell too much on league tables because all league tables are rubbish. I mean, every university will come up with their own version of a league table. Obviously, Edinburgh comes up with one where we come top. I mean, this is the one on the left is a measure of research power, which is kind of the amount of research you do times how good it is. And because we're very big, we come top. The one over the other side is kind of a teaching scale, you know, that goes up and down for every year. When we're a little bit down this year, I mean, it doesn't really, we're not doing much different from going from 4th to 11th. But we usually perform quite well on these things, but they are somewhat meaningless. If you're choosing a degree to go to based on league tables, then yeah, good luck to you. So we're going to have a look now at some of the individual degrees that we teach within the Earth Sciences part of the School of Geosciences. I should just point out that there are other degrees that you might also be interested in geography, so we have a couple of different geography degrees. There's also if you're interested in geophysics and meteorology, there's also a physics and meteorology degree as well, which is very similar. It just has less about the Earth and more about just the atmosphere and physics. But if you're interested in either of those, then come and talk to us at our stand in the Sanderson building, or the physics stand in this building. Pointing out here, so some of the terms that get bandied around with earth sciences and geology and geosciences and environmental, there's quite a lot of overlap between these two. So this Venn diagram, it's an Euler diagram, not a Venn diagram, but this Venn diagram would look different in different universities. But just to point out that if you do a geology degree, you'll be doing other things as well, lots of other areas of investigation science. So geology. So it's a degree for people that are interested in understanding the solid Earth, okay, from I guess also including kind of the atmosphere and the oceans a little bit. So it's for people that are interested in things like volcanoes, the history of life on Earth, how did the planet evolve, how did it form, how did life develop on it to keep it habitable through kind of billions of years of its existence. But it's also looking at the modern processes, so it's looking at things like natural hazards, you know, which regions are more susceptible to earthquakes, okay? Which kinds of volcanoes are more hazardous than others? What might cause a volcano to suddenly, you know, change from being just erupting quite passively to being an explosive eruption? So understanding the physical, the chemistry, and the biological processes of the Earth and how they have changed through geological time. So if you Wordle kind of the geology Wikipedia page, these are the kind of things that you get. So you're looking at rocks, looking at sediments, looking at the processes of kind of the formation of those things and how we can make observations and then interpret the geological evolution of an area. The environmental geosciences degree starts out being very similar to the geology degree, except its focus moves from being interested in the solid Earth and the physical processes of that into the interaction of the solid Earth with the biosphere. So it's interested in climate change, environmental change. It's interested in things like the cycling of nutrients, things like nitrogen and phosphorus, which ultimately come from rocks or the atmosphere, and how those become biologically available, how they get used up, and how they get exported back into rocks and join the kind of the rock cycle. So it brings in aspects of chemistry, biology, and the environment. And we go to Jamaica, which is pretty good fun. So you Wordle that, and you can see that it's quite a lot of the same words are coming up, but it's got this little bit more of an environmental kind of tinge to it. The Geology and Physical Geography degree, once again, starts out being very similar to geology, but its focus shifts from the solid earth to the surface processes. So it's interested in how sediments get moved around on the surface of the earth by rivers and windblown in the ocean, and how that impacts hazards. So you might, an example might be if it's a big earthquake in the Himalayas, lots of landslides slide into rivers, that produces a big pulse of sediment. How does that sediment move down the river? How does that change the morphology of the channel as that sediment pulse is moving through the system? And therefore, how does that affect the flooding risks? If you fill your river up with sediment, it then becomes much more susceptible to flooding. It includes things like glaciology, understanding how glaciers have carved out the landscape, but also how glaciers are responding to climate change. It has a huge component of remote sensing, so using satellite information to infer things like ice mass in the polar regions. And there again, it's, I guess, geography forms a big part of geology and physical geography. So if you're liking physical geography at school, maybe this is for you. So the geophysics degrees are a little bit different. We'll come on to how different they are from our geology degrees, but they're really degrees that are really developing you as a very quantitative scientist. So if you are interested in physics and maths and want to understand how the Earth works, this is the degree for you. So it's a very quantitative, highly numerate students tend to get drawn toward this degree. But it's also, has these different flavors. So it can be more geological if you do with geology, or it can be more climate science related if you do the geology, geophysics and meteorology. So if you want to understand how the atmosphere works and how that is responding to environmental forcing, how different environmental pollutants are cycled through the atmosphere, so things like nitrous oxide and things like that, how the physics and chemistry of the atmosphere impact on that environmental hazard. And again, okay, so much more diversity here in the number of kind of words in the Wordle here. Okay, so it includes much more kind of physicsy terms like gravity, electromagnetism, which are tools we use to look at the Earth using the physics. So to summarize the structure of our degrees, we have a 2-year pre-honours where we basically get the fundamental grounding in the subjects. There is an option to fast track that into a single year and condense down all of the core courses that you have to do into 1 year. But either of those two options, none of that counts. You just have to pass those 2 years to make it into the honours years, which are usually just year 3 and 4, but with most of our courses, except environmental geoscience, there's this integrated 5th year master's option. And these grades count towards your overall degree. The 3rd year, there are many fewer options here, and that's all about effectively preparing you for your independent dissertation in the 4th year. Okay? And also preparing you for the option courses in the 4th year, where you go into much more detail and are effectively being researchers. The 5th year, I guess, carries on from the 4th year. You would do an additional research dissertation, which goes into much greater detail and depth and takes up more of the credits for the year. And you do master's level courses as part of that 5th year. So looking at the pre-honours for the geology, environmental geoscience, and geology and physical geography degrees. So the first year, you'll have some core courses, okay, and you'll have some option courses. And you'll notice that the first year is identical for all of those 3 degrees. So we've got some course in Earth Dynamics, course in Introduction to Geological Record, course in Evolution of the Living Earth. Now, those words might not mean anything to you, but basically these are introductory courses to the Earth system, how we observe it, okay, and how it's changed through time. We also have a maths course for people that haven't done so much maths. Then the final option courses are whatever you want. They can be other Earth science courses, they can be other physics courses, or they can be, French, history, anything. The second year, you then start to specialise a little bit more. So you start to specialise down. The geologists will do an extra degree looking at the relationship between rocks and the environments in which they form. So how can we then interpret from the rocks whether it was a rapidly subducting region, was we're getting lots and lots of accommodation space, or was it in a region of compression, or we were getting lots of volcanism? So understanding from the rocks the environment. The environmental geoscience degree has a course in oceanography, understanding how the oceans work from a physical and a chemical and a biological basis, and the geochemistry of the Earth system. So the environmental geoscience course starts to become a little bit more chemical than the others. And then the physical geography course brings in a course in geomorphology, so understanding landscape evolution and landscape hazard from observations of shape. The geophysics degrees, you can see, are very different. So they basically start off being like physics degrees. They have the same courses as a physics degree, maths for physics, physics, maths for physics again, and more physics. But there are no options in the first year because we take up the physics options courses with introductory geology courses. And then again in the second year we start to specialise, so the meteorologists will do more meteorology, the geologists will do more geology, but there's also a core of maths and physics courses. So I'll skip over some of these details, but basically the third year is all about reducing the number of options and ensuring that you have the right skills and knowledge to move on into the fourth year, where every course does a research dissertation, which for geology is usually built around a mapping expedition that students go on, whereas the other degrees have more flexibility in the kind of thing you'll do. So you might be still going out in the field, collecting some samples, bringing them back, making measurements on them. You might be doing some computer modelling. A huge variety of things are available to you because of our large kind of base of staff. So I've mentioned that the field is an important part of our teaching, so we go to kind of all these kind of places in Scotland, which are fantastically fun to go to and very convenient. We also go to places that are not in Scotland, which are also pretty exciting and fun. If you come to the stand, we've got a field brochure guide to kind of talk you through all of these different places we go to. There is an opportunity for international exchange, usually in the third year, where we've basically already set up exchanges with different universities around the world. You don't have to go to these places. You can set up your own exchange going to a university anywhere in the world. We just need to make sure that the courses that you do when you go away match what you do, what we're doing in Edinburgh. Because the third year, if you do go away, the marks for the third year don't count, and your whole degree is then based on your fourth year marks. And if you've not been prepared for those courses, then bad times. So there's also benefit for students that don't go abroad, because Edinburgh is such a popular destination for exchange students. You do get that cultural exchange by staying in Edinburgh and the world visiting you, because the world does come to Edinburgh. I guess there are lots of different kind of teaching styles as well. We do lectures, we have practicals, we have a lot of field trips. I won't dwell on this too much, just to point out that there is this example lecture at 2:50 in the Swan building. Come to that, it'll be fun. But we basically make our assessments not just kind of lecture, exam, lecture, exam, lecture, exam. We do a huge variety of different types of assessments. So there'll be project work, there'll be group work, there'll be independent work, there will be exams and tests. But we try and vary it as much as possible, so it suits a wider range of students. Which comes out of this, basically, this Institute of Academic Development, which is an organisation which exists in Edinburgh but also serves universities elsewhere. So it's the thing that provides helpful things like study support for students and stuff like that, but it also helps improve our lecturers' lecturing. Okay, so we have lots of kind of different courses which lecturers can go on to help develop us as educators and teachers. And it's really good to have this kind of service within Edinburgh, because it's a lot easier for us to engage with it. And it's becoming more and more part of kind of my life as a lecturer, learning how to do it better. Just quickly on student support, there are probably presentations on this elsewhere today, but there are kind of three branches. So there's an academic support network, and that will be your personal tutor, but also the personal tutor will advise you in what courses might be good or bad for you, will make sure that you're not failing. The students can also go directly to the Institute of Academic Development for particular study skills which they might need improving on. We have a network called GeoPals, which is peer-assisted learning. So the staff don't really have so much to do with this. It's really second, third and fourth years kind of running sessions for first and second years in terms of study skills, but also specific help on things that they thought they would have benefited when they were students. So it's a very good way of students kind of getting what they need because they're giving it. We also have a wide network of pastoral support, so your personal tutor can help in this regard, but we have dedicated student support coordinators within the department, as well as the university and students' union provided stuff. There's also a huge amount of IT support, our IT unfortunately called IS, but basically don't buy any software before you turn up for university because you'll probably get it for free when you rock up. You also get a bunch of online storage as well. Okay, coming to the stand and talk to us about careers. We have a wide variety of things our students go into. Our students are quite employable. We also have a dedicated person in the careers service that just deals with geosciences students, arranging things like internships and CV writing and basically preparing you for the world of work. So just quickly, I'm going to talk about our offers. So you can come and chat to us at the stand, but typically we're after lots of A's for hires or A-levels. We do go through clearing. The rules for who we go through clearing for will change every year, but particularly if you're from a disadvantaged neighbourhood in Scotland based on postcode, there's an extra block of places available through clearing for you. There's definitely flexibility on grades for our UK students doing A-levels or overseas students. It's just the way that the funding situation works, unfortunately. So definitely, if you apply and you just missed your offer, then ring us up on the day and we'll sort you out. So very briefly, why Edinburgh? Okay, so lots of reasons to come for Edinburgh. We're a pretty good place. We're big. We're good. We've got really flexible degrees. But the main reason to come to Edinburgh is because it's a fantastic city to live in as a student. It's a really fun place to be. And it's also in Scotland, which is awesome. So here endeth the lesson. If you have further questions or want to chat to some of our students, we've got students at the stand on the Sanderson building. We're not running a tour today because our building is being built with builders in. But you can come and have a chat to some of the lecturers or the students at the stand in the Sanderson building, which will be going all day. And there's a lecture at 2:50. So come along to that. It'll be fun. And I'll be there to answer questions as well if you have more questions. But I think I'm being thrown out. I am being thrown out of this room. So if you could leave by the exit door down here, that would be super awesome. Yeah! Woo!